All right, so here's our final lesson in the chemistry portion of physical science. And this is going to be on radioactivity and nuclear decay. So we have two main types of nuclear decay. We have fission and we have fusion. Fission occurs when a nucleus splits into two or more smaller nuclei. So it is the splitting of a single nucleus into two or more smaller nuclei. Some of this mass is going to be converted into energy. Law of conservation of mass. Mass is not created or destroyed. It simply rearranges. All right, so there is some energy mass which gets converted into energy. Now, fission is how nuclear power plants work. So we're able to use nuclear power plants in order to provide energy in the form of electricity. And what we do is we take uranium-235 and we take N for neutron. Now remember, N has a mass of 1, so there's the mass of 1. All right, N is neutral. All right, so it does not affect the atomic numbers. So the mass number is on top. The atomic number is the protons. N doesn't have any protons. There is 0, but the way I remember that's a 0 because N is neutral. It's just how I remember it, but it really is because a neutron is not a proton. So we take this neutron and we hit the uranium-235. When this uranium hits the uranium-235, it's unstable and it creates this self-feeding reaction. It breaks uranium down into barium-141 and krypton-92, and it provides us with 3 new neutrons. These neutrons are then able to come back, hit more uranium to create more products. Energy is being released as a process. All right. Fusion. Fusion is the process in which we combine 2 nuclei and to make 1 nucleus, which is larger. And now this makes sense. If I put 2 things together, I'm going to get 1 thing that is bigger. And this is going to provide even more energy than fission. And this is going to occur naturally in stars. So this is why the sun produces so much energy, because it actually is happening by the process of fusion. All right, so Mother Nature's already figured out how to get fusion started. She's already figured it out. The problem with fusion is we have not yet figured out a way to get fusion to start. The amount of energy needed to get fusion to start is so great. We haven't figured out a way to overcome that. Mother Nature has already figured that out. We got stars, which fusion occurs from, and the sun does heat the earth, okay? So what are the main differences in fission and fusion? All right, fission, this is going to be our nuclear power plants. It uses uranium-235, but uranium-235 is a limited resource. Once it's used up, it's used up. Fusion uses hydrogen gas, and hydrogen gas is abundant. Now remember, hydrogen, one by itself, is diatomic, H2. Fission. Fission is pretty dangerous. There is a danger of a meltdown. There's a danger of it overheating, the nuclear power plant overheating and causing what we call a meltdown, where there's a massive release of radioactive material and gamma rays and all kinds of stuff. It could create lots of problems. All right. Fusion doesn't have this danger. Fission also creates a lot of toxic waste, all right? And this waste is very toxic and it's still radioactive. It can still harm the environment around us. So the question becomes, what do we do with this toxic waste? All right? And the answer really is we don't know what to do with this toxic waste. It either gets dumped in these deep, big, huge caves, or like deep in the ground, maybe gets thrown out way out in the middle of the ocean, which is obviously not a good thing. We don't want to do that because there's little fishies and all kinds of life swimming in the ocean. So toxic waste in the ground can leach out into the ground and cause danger to the wildlife around it. So what do we do with it? There's a problem with that. And maybe you can move on when you get out of class, out of school, and you can do something with that. You can do something and maybe make that your life's work. What do we do with that toxic waste? Come up with a way to maybe make it not toxic, or who knows? Y'all, the possibilities are endless. Y'all are going to do great things. Fusion. We don't have any toxic waste. Okay? So, fusion is actually safer than fission, so it seems. But the reality is we can't get fusion to start because the amount of energy needed to get it started, we haven't figured out that way. So maybe that's something you could do with your life as well. You could become a scientist and try and work on fusion, make that your life's work. All right? Fusion is not yet sustainable. All right. Now, fission produces a lot of heat in the process, so we end up with what we call thermal pollution. And thermal pollution, you may have learned in earth science, is where the temperature of the area is higher than what it should be, all right, and it can cause devastation to the wildlife because we do know that life is adapted to the environment in which it lives. So if we heat up that environment, that wildlife may have a difficult time surviving. So thermal pollution is causing that heating of the area around the nuclear power plants and can cause a lot of problems. So radioactivity. Radioactivity is the emission of high energy radiation from the nucleus of an atom. So the nuclei is just another word for nucleus, all right? So when we talk about the nuclide, we're talking about the nucleus of that isotope. And remember, isotopes are atoms that have a different number of neutrons, all right, where neutrons are, this change in the number of neutrons is what makes it unstable. An isotope has a different number of neutrons, same number of protons and electrons. Okay, reviewing back from previous units. All right, let's talk about the different types of radioactivity and radiation. We have three main particle types: alpha, beta, and gamma. Alpha is a helium nucleus. Now, alpha, if it is a helium nucleus, let's look at its symbol. Helium is He. It has a mass of 4 and an atomic number of 2. So there's our symbol, all right? And we've already learned in the previous unit how to write symbols for isotopes. All right, now helium nuclei, they are really large and slow moving. So air around us, if I was to shoot alpha particles at you, the air around us or paper would be enough to simply block those alpha particles from reaching you and causing damage because they are so large and slow moving. They do have a positive 2 charge. Beta particles are electrons. Now our symbol for beta particle is going to be a 0, -1, E for electron. All right, now we do know electrons are negatively charged, so that's a 1- charge. We've learned that in previous unit. Now beta particles are a little smaller than alpha particles, therefore they move a little quicker. All right, so things like leather and foil and plastic are going to protect us from beta particles. If I was to shoot beta particles at you, leather, foil, or plastic would be enough to protect you from those beta particles. They can't penetrate through these items. Beta particles can't penetrate through, so you would be protected. Gamma is the big one. All right, this is the real high energy photon. And this is going to have a symbol that looks sort of like this, a funky Y. All right, I call it the funky Y. It has an actual name, but all right, our gamma symbol. Now, these are such high energy particles. The only thing that can protect you from this is concrete and lead. All right, so this is why if you've ever been to the dentist, they put a lead vest on you. If you've broken a bone and you went to the orthopedic for an x-ray, they put a lead vest on you. All right, x-rays create such high energy photons. This energy, we only want it to be concentrated right around where the x-ray is. So we're going to protect the rest of the body with a lead vest out of an abundance of safety precautions. And if you've ever noticed, if you've ever had an x-ray done, the x-ray technician leaves the room or goes and stands behind a wall. That wall is actually going to be made, it's got concrete and it lead or lead, and it protects them from any rays that are being emitted. Now, having an x-ray done every once in a while on your teeth or something like that, or if you break a bone, that's okay. We just don't want to be exposed to it all the time, all right? And those x-ray techs are there doing that day in and day out, so they have to protect themselves. And then out of an abundance of caution, we're still going to protect you while we're sending those high energy photons your way to check out your teeth and bones. So why do nuclides decay? They decay because they are unstable. They need to have a ratio of neutrons to protons that is stable. So if I change the number of neutrons, I have a different isotope, but changing these neutrons also makes it very unstable. So they will begin to decay to form a stable form. So potassium with a mass of 40, potassium 40, it has 19 protons. And in this case, it has 21 neutrons. It is unstable. The stable version of potassium still has 19 protons, because remember, protons are what make the element. So if I change the number of protons, I change the element. But in this case, the neutrons are 20. So 20 neutrons for 19 protons is a stable isotope of potassium. So when I changed the number of neutrons, potassium also became unstable and therefore radioactive. Now, when radioactive decay occurs, it occurs by what we call the half-life, and this is the time it takes for half of a sample to decay. Now, we measure radioactive decay by how long it takes for half of that sample to decay. The reality is radioactive decay is a process. It is continuous, all right? So it always is continuously happening, but ultimately we measure it by how long for half of that substance. And now this is something that we talk a lot about in AP chemistry. We talk about it as talks about kinetics and first order rate law reactions. So there's a lot of science behind it. All right, which if you really like chemistry, you can always move on and take more chemistry later. All right, but radioactive decay is an exponential decay because as half decays, all right, over time, eventually you're left with almost zero. Now, different radioactive elements have different half-lives. All right, so polonium-194, it doesn't even take a single second for half of that sample to decay. Iodine-131 takes 8 days for half of it to decay. Carbon-14 takes over 5,000 years, and uranium takes 4.5 billion years. And now again, this number right here is not a made-up number. We can actually do some scientific calculations, which we do in AP chemistry, to show where these larger numbers come from. All right, so keep that in mind. Yes, it is true that a single human being can't live 4.5 billion years to see that half of the uranium-238 decayed, but because it's a continuous process, we can do some measurements and some calculations in order to figure that out. Okay, so these numbers aren't made up numbers, there's science behind them. If you ever have a contrast done in the doctor, they will use oftentimes like radioactive substances, like radioactive barium, radioactive iodine. Now, these guys have really short half-lives. That way they are out of your system really quickly and don't cause a lot of issues.